So basically, we're going to create a time series forecaster on the unemployment rates data using LSTM. All right. So just to save us some time, I've already imported the packages we need. So while the packages are running, we can then go ahead and set up the program or create a function to extract data from the Federal Reserve Economic Database. What I've done here is, so basically I've created a function to fetch the data from the Federal Reserve Economic Database. So, and this is a URL, and the series ID will be plugged in here. So since for this project we are just extracting the unemployment rate, so what you can basically do is you can just, this is the series ID for the unemployment rates. So once you run this function, it will basically plug this unemployment rate here automatically. Then it will pull in all the data for us. So if I run this, there is some issue here. Oh, okay, so yeah, now if I run this, it gives us a data set with 919 rows and one column. Okay, so basically, let's just visualize the data. As you can see, we have the data we need. It starts from 1948 and it's a monthly data for starts on the 1948 January 1 and it goes up to, let's say, around till July 2024, which is just last month. Okay, so now since we have this, we can then now move to pre-processing the data, which is what we are going to do right now. Okay, so basically the data is zero null values because there is basically every month data we need. So we can just go ahead and set the next one in which we will do a little bit of more pre-processing. Then we can split the data into train and test so that we can move on. So alright, so basically what I've done here is I've added something called scalar, which is the min-max scalar, to scale our data between 0 to 1, because neural networks can only take in numerical values in 0 and 1. So this is very important in order to do that, to feature feature the images into zeros and 1. Then we create a function called sequences. So basically what a sequences do is that, so it prepares our data for the LSTM model. The function basically creates a sequence, creates sequences of 12 months, which is the sequence length I've mentioned here, to predict the next month. So basically what it will do is that if it has to predict the month of August, it will take 12 months before the month of August and it will predict the next month. So if it has to predict them for the month of June 2025, let's say, it will predict the like previous 12 months, which should end at May 2025, and it will predict June 2025. So that's exactly what that does. Then we are basically splitting our data into the train and test plate, the normal usual way. So that's exactly what I've done here. So now let's run this code. Alright, so here I made a mistake here. So it's basically scale data and it should be the sequence length. I should run the two arguments within them. Alright, so now the script has finished running this particular section. Now we can move to the next section, which is building the LSTM model. So building the LSTM model. It's a very simple, building models are very simple, honestly. Getting the data and pre-processing them is the biggest part, if you ask me. Alright, so basically what we are doing is that we create a sequential model with two LSTM layers. As you can see, this is the first layer and this is the second one. So basically if you want, you can just put it here. So two layers. The first LSTM layer is 50 units using rel activation and returns sequences for the next LSTM layer. And the next LSTM has again 50 units and activated by rel, ReLU activation basically. So, or rel. And we have something called the dense layer has 1 unit for a single output, which is next month's prediction, which is the next month's unemployment rate prediction. Then all we have to do is that compile the model. We are using an optimizer called Adam to help us with compiling, and we are using mean square error as a parameter for our loss function. All right, so let's run this. All right, so that is good. Now let's go ahead and set up the factors to train the model. Alright, so what we are doing here is we are training the model we brought in our splits basically. Then we are training the model for 100 epochs with batch size of 32. Now we use 10% of our training data for validation, which is what it says 0.1. Now I also wanted to add something here, so let's just create a visualization for training and validation loss, okay? So alright, so that okay, let me just add a title also here. So which should be training and validation last shot. Now if you run this, it will basically train the model for 100 epochs. As you can see, it's already pulling till 15, 18, 20. It's pretty fast. So we're at 50 already. Alright, we are at 94, 99, 100. Yep. So as you can see, this is the chart we have. Yep. So that's a beautiful, insightful chart for the training and validation loss. So what we'll do is that we will then create we'll just basically evaluate the model just to understand where we stand in terms of performance and everything. Alright, so basically what I've done here right now is we have basically used our trained model to make predictions both on the training and test data. So that's exactly what goes on here. And we basically then inverse transform our predictions to get back to the original scale. And then we calculate mean square error, mean absolute error. So as you can see here, then we calculate mean square error, mean absolute error, and the R squared for both training and test sets. And so basically, so that these metrics can help us understand how well our model is performing. So basically, let's run this out. As you can see, these are the outputs basically. So what's happening here is that, so in general, R2 is a metric used to evaluate the model performance. Okay, so on the training set, the model's performance was at, let's say, R2 of 0.98, which is high and which is really good. But when it comes to the test set, the performances was at 0.82, which is less than the training set, but it's still better. It's still a better performing model. So the other one is, so the mean absolute error is the difference in the actual value and the predicted value. So as you could see, in general, in the test data, it's the prediction is off by 0.28. What it basically means is that the model's prediction, the model's predictions are off by about 0.25 percentage points. That's exactly what it means. But that's still a very short percentage point difference, so that this model is still feasible and very highly effective. All right, now it's time for us to visualize the result. When I say visualize the result, we are going to predict the next 12 months, let's say, in a chart format so that we can understand what the unemployment rate is going to look like based on the performance of this model, which is pretty accurate. Like I said, it gives us almost 82% efficiency or performance rate. Okay. All right, now let's run this. Yep, so that's the chart we have. So basically, if you could zoom in, you see the labels here. So it is pretty closely aligned with the time series chart, the actual training and test time series, which actually means the model is really good. And we also saw the metrics here on numerical terms on how the model is good. And this is just a visual aspect to understand how the model is good and how it performs really good. So basically, then let's plot the future predictions that I promised you. Alright, so it's running right now. And yep, the error with this. Alright, so once it finished running, as you can see, the future prediction is it's going to be in a. I hope you guys can see it. Yep, so it's going to be in a uptrend, but the visual is not that great. So let's ask it to print the information as well, which is we are trying to start print the information. Just text numbers. Alright, so now when I run this, you could see the predictions. For the month of August 2024, it says that we'll be at the unemployment rate of 4.32%. And for the month of September, we'll be at 4.44. So basically, it's going uptrend and a steep high is what the model recommends. See, one other thing is there's a lot of ways you can improve this model too. Now it makes almost efficient prediction with the R-square of 82. But one easiest like tuning you can do is that you can basically ask it to increase the sequence length, which we set to 12 months initially here, to we can increase the sequence length. So basically what you will be asking the model to do is that instead of just looking at the previous 12 months to predict the next month, look at even more months in the history. So let's say if I change it to 48, let's say, right? So you're basically asking the model to look at more data before it actually predicts a newer model. So that will actually can improve the model's performance. So basically, uh, run this, but make sure if you change these kind of tunings, then you have to rerun the model again. So let me just quickly retrain the model. So when I say retrain is what I mean. Alright, so now the model is trained on the latest sequence length which we asked the model to do. Again, the training validation loss looks clean because there is not a lot of discrepancies there. So now let's evaluate the model again, okay? So if I run the evaluation, ooh, now if you see the model's R2 actually went down even further. So that is where, see, training these models is involves a lot of trial and error. So you have to find that perfect sweet spot where the model actually performs good. So what I'm gonna do is that I'm gonna now change. I mean, it's not like only changing the sequence length is not like it's the only way to tune this model, but just to there are several other hyperparameter tuning you can do. I'll add this code to my GitHub and put the link to my GitHub in the description below. You can just check it out in case if you want to repurpose this code.